Exercise 6C, proof by contradiction. So in this exercise, we're learning about proving statements using contradiction. And what you need to be able to do is contradict a statement, prove its falsity, and then hence prove that the original statement is true. Now, how do we prove by contradiction? You'll notice that there's not much of an explanation before we get into the examples, because it's more of a logical way of being able to prove that something is true. There are some statements, such as this one in example 9, where you can't really do a direct proof. So for example, it says, prove that no quadrilateral has more than one reflex angle. Are we really going to go through every single possible iteration of quadrilateral? Like, are we going to change all of the angles by a degree or half a degree and prove that? No, it's impossible to do that. So instead, we're going to kind of think of the opposite, a contradiction to it. So instead of saying that no quadrilateral has more than reflex angle, let's assume that there exists a quadrilateral with two or more reflex angles. So you can see that this is a contradiction, or it's really the opposite of this original statement. You can almost think of it as negating the statement, kind of like what we did in the last exercise, but you'll see that the language is different. Now, same idea as the last exercise. If I can prove that this contradicted statement, so the opposite statement, is false, then that would say that the original statement must be true. So let's assume that there exists a quadrilateral with two or more reflex angles. If I can prove that that is not possible, then that must mean that there is no quadrilateral that has more than one reflex angle. So this is how you essentially prove using contradiction. You create a statement that is the opposite, and then you prove that it doesn't make any sense. It's a false statement, and if it's a false statement, then the original must be true. So if there is a quadrilateral with two or more reflex angles, let's just focus on two reflex angles. We know, as the question has said, that a reflex angle is 180 degrees. If there are two of them, then those two angles will add up to 360 degrees. Now, this is a problem for us because a quadrilateral, which has four angles, all need to sum to 360. So how is it possible that only two of them sum to 360 if there's still another two to go? It doesn't make any sense. So this here contradicts the fact that the quadrilateral must sum to 360 degrees with four angles. Therefore, there can only be one reflex angle, because when we tried to do more than one, we could see that it didn't work. So that's how proof by contradiction works. That's kind of like the example of how it works and how we do it. So here's a bit of a breakdown in terms of what you need to do. So the first thing we do is that we assume that the statement we want to prove is false. Then we show that this assumption leads to mathematical nonsense, as in it just doesn't make sense, that the contradiction is false, whatever it might be. Conclude that we were wrong to assume that the statement is false, and then if that statement is false, then the original one must be true. So we've written a false statement, a false version over here, and then we prove that instead. We try to prove it. We end up at a point where it just doesn't work. It's going to break down, and when it breaks down, that means that the original statement must be true. So let's go ahead and try another example. Example 10, we've got a Pythagorean triple. It consists of three natural numbers, a, b, c, and it satisfies a squared plus b squared equals c squared. Show that if ABC is a Pythagorean triple, then ABC cannot be all odd numbers. So again, I'm not going to go through and test out every single odd number or even number to see whether this is true. So instead, let's assume that this is false. So the opposite of that. So let's assume that A, B, C are all odd numbers. Let's assume that they are all odd numbers. So we're doing the opposite. If they are all odd numbers, then we have a squared plus b squared. So we know that when we square an odd, we end up with an odd. So that'll be an odd number. Square an odd ends up being odd, and an odd plus an odd is equal to an even number. So a squared plus b squared is even. Now, on the other side, c squared, again, when you square an odd, you end up with an odd. So c squared must be an odd number. So then a squared plus b squared equals c squared means that I end up with an even number equal to an odd number. That there is our mathematical nonsense. That is false. It can't happen. Therefore, this statement that we made must be false, and hence the original statement must be true. So we can write, therefore, A, B, and C cannot all be odd numbers. So we're writing the opposite, proving that it breaks down. Since it breaks down, the original statement must be true. All right, let's try this one. So suppose that x satisfies 5 to the power of x equals 2. Show that x is irrational. So again, really difficult to prove this. Let's use the contradiction. So let's assume, or let's suppose, that x is rational. Now, if x is rational, then x, maybe I'll write that on this side. If x is rational, then x can be written like this, okay? Because we know that all rational numbers can be written as a fraction, where both m and n would be natural numbers. I suppose they could also be integers. There's no reason why they can't be a negative number, but either way, they have to be whole numbers in this case in order for it to be rational. So let's go ahead and apply this statement. So if we have 5x is equal to 2, 5 to the power of m and n is equal to 2. Let's try and simplify this a little bit further. So I'm just going to get the n to the other side. So I end up with 5m is equal to 2n. Now we know, as we said beforehand, that any odd number to a power will always give me an odd, and any even number to a power will always give me an even. So what I end up with here is an odd number is equal to an even number, which is false. It's a contradiction. It won't work because it just doesn't make any sense. So because that breaks down, therefore x must be irrational. So again, getting the opposite statement, assuming or supposing the opposite statement, making it work, so carrying on as though it's a direct proof, but then you always get to a point where it's going to break down. Because it breaks down, that means the original statement must be true. Now this one's a little bit more of a fun one. It's to prove that there are an infinite number of primes. Now, never would you be asked to do a question like this, just coming up with it on your own. This is actually more of a proof, a famous proof that was shown by a famous mathematician, and we're just going to go over it today, but I would never expect you to have to do this on your own. So it was, if you've heard of Euclid, about 2,300 years ago, created this proof. And I'm going to do my best to try to explain it because it is a little bit tricky. So it proved that there are an infinite number of primes. So with a proof by contradiction, remember we always try to get an opposite statement. So suppose that there are a finite number of primes, so the opposite. So instead of infinite primes, I have a finite number of primes. So if we were to write a list, that would kind of be like this: 2, 3, 5, 7, blah, 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 all the way to the infinite number, to the final number, which we're going to call p. Now, here's a little bit of a trick that Euclid did. He created a new number, which I'm going to call n. And the way he created this new number is he went ahead and multiplied every single number that is in this current list, so all the way times p, and then he decided to add 1 right at the end. And that creates a new number. It's just a brand new number, and we know obviously there's an infinite number of numbers, so there's no reason why that can't have been created. Now here's the interesting thing. If I had created this new number, I could go ahead and divide it by any number of these primes. So if I decided to divide this number by 7, that's fine, because 7 clearly goes into it. Even if I decided to divide it by p, that's not a problem. It clearly goes into it. It is going to leave over a factor of 0. But because I added 1, there is no number in this list that is actually a factor of this particular number. There's no number here that can possibly fit into this without giving me a factor of 0. So it's always going to leave a remainder of 1. So n is not divisible by any of the primes. Any of the primes. Now, I mean, you can kind of think about it, it's not really divisible by any number then, because if it were divisible by any of the primes make up all of the other numbers. So that's why all we need to really think about is the primes. So n is not divisible by any of the primes since it leaves a remainder of 1. Leaves a remainder of 1 when it ends up being divided by any of those numbers. Now here's the problem. If it's not divided by any of these primes, and obviously that then means it's not divided by any other number, then shouldn't it also not be divided? Well, that's sort of, sorry, I went to go on and say the same thing twice. It can't be divided by any number, except obviously you can always divide by 1. What does that mean as part of the definition? Since it's not divided by any other number, the new number n, or I could just write n, must be a prime number. So I've just now created another prime number. So that tells me that my initial assumption, or what I've supposed is that they're a finite number, that's not possible anymore because I've just created a new number that is n. What this does is it contradicts this statement that that there are a finite number of primes. So whether you kind of got the hang of this or not, it is a difficult proof. Again, I would never expect you to have to do anything like this, but this is something that one of the mathematicians has done, and I've just tried to replicate his findings. So just in the final statement, n must be a prime, hence there are an infinite number of primes, because I can always just go ahead and do that same trick, add 1 and say that's a new number that's been created that cannot be divided by anything before. There are an infinite number of primes. All right, that's it for exercise 6C. So go ahead and enjoy proving by contradiction.